chair, Dr. Evil.
Thank you. Whoa! Thanks. So you're the...
By the way, I realize that I have a large mole on my face.
Where? What? Where's that mole? I didn't see one.
Jolly good work.
Yes, nice to mole you. Meet you. Nice to meet you, mole. Don't say mole.
Stop.
I said mole.
Stop. Bye.
Mole. Mole. Mole.
Oh, shut up!
Mole, 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 mole.
The mole is a unit of measurement that you guys know all about. 98% of the time in this class, if you have grams, you're going to convert it to moles. It's a unit of measurement that we tend to use quite a bit, defined as the amount of a substance that contains as many elementary entities, that could be atoms, molecules, ions, electrons, it could be particles, whatever, as there are atoms in 12 grams of carbon. The number of atoms in 12 grams of carbon is 6.02 times 10 to the 23rd, and you guys should know that one as Avogadro's number. Okay, this is the mole map. Some people like to use the mole map. We've got moles. You can go from moles to grams, moles to liters, and moles to particles. That could be, once again, atoms, molecules, ions, whatever. If you're in the mole hole and you're going from moles to grams, you're going to multiply. If you're going from moles to liters, you're going to multiply. If you're going from moles to particles, you're going to multiply. If you're going grams to moles, or liters to moles, or atoms, let's say, to moles, you will divide. Okay? If you're going grams to moles, moles to grams, you're going to multiply or divide by its molar mass. And of course, you get that from the periodic table. If you're going moles to liters, liters to moles, you're going to multiply or divide by 22.4 liters. That's, of course, at standard temperature and pressure. And if you're going moles to particles or atoms, molecules, what have you, particles to moles, you're going to multiply or divide by Avogadro's number. There's another mole map that's very similar to this. We've done this already. We've done grams, liters, and particles, but you can also add solution volume, like liters of solution. Now this one's a little bit different because if you're going from moles to liters of solution, you're going to divide by molarity. If you're going liters of solution to moles, you're going to multiply by molarity. So there is another one, but it doesn't follow the same pattern of multiplying as you go away and dividing going in. Okay, I typically prefer to do the dimensional analysis way instead. I like to start with my grams over 1, convert grams to moles, and then moles to atoms. For example, 6.022 grams of hydrogen gas. 1 mole of hydrogen gas is 2.016 grams, and then 1 mole of hydrogen gas is 6.02 times 10 to the 23rd molecules of hydrogen gas. This is the method I prefer, whatever works best for you. Empirical formula, we're going to be doing quite a bit of that in AP. Here are the steps. If I give you the mass percent in elements, for example, 24.7% potassium, 34.7% manganese, and 40.5% oxygen, how do you go to its empirical formula? And the empirical formula is the simplest ratio of atoms within the formula. So what you do is you drop the percentage and you write grams, because if it's in percentage, you can already assume that there's 100 grams. So for example, 24.7 grams of potassium, 34.7 grams of manganese, 40.5%, or excuse me, grams of oxygen. Like I said earlier, 98% of the time, if you have grams, convert to moles. So convert all of them to moles. Then you're going to do your mole to mole to mole ratio by dividing them all by the smallest number. Okay? So down here is this just showing you that this is the empirical formula, C1H1, but its true molecular formula for benzene is C6H6, and it weighs 6 times greater than its actual empirical formula. Glucose has an empirical formula of 1 to 2 to 1. Its actual molecular formula is C6H12O6. So if we took this guy right here and tried to solve for empirical formula, the first thing I would do is drop the percentage and write grams, grams, and grams. Convert grams to moles, grams to moles, grams to moles. That's going to give me 0.632 moles of K, 0.632 moles of manganese, 2.53 moles of oxygen. At this point in time, I'm going to divide them all by the smallest number. That's going to get me a 1 to 1 to 4 mole ratio. Like that right there. Okay? If you ever get something that's like a 1 to 1 to 2.5 ratio, then you're going to have to double everything.